Good morning, everyone. Welcome to the Warren Lecture Series. Today's speaker is Professor Stefan Llewellyn Smith. He's a professor at the Department of Mechanical and Aerospace Engineering of University of California, San Diego. Stefan received his PhD from University of Cambridge in 1996 in applied mathematics. Then he was a research fellow at Queen's College for 3 years, and did some postdoc at Oceanography Institution in La Jolla. He's also professor at this institution. Stefan joined the department in 1999 as an assistant professor. Now, as I said, he's a full professor. His interests are in fluid dynamics with application to environmental and engineering problems, acoustics, asymptotics method, and he is also an associate editor for Science Journal of Applied Mathematics. And with that, I will not take more time. Please join me in welcoming Stefan to the department.
Thank you very much, Sonia. Please let me know if you can hear me, since I'm wearing a mask. So it's a great honor, pleasure to be invited here. I have not been to this department before, and I hope I can tell you some things about what we've been doing that you might find relevant and interesting. And so I'm starting off with a picture of Lake Superior. This was taken by Todd Christopher, whose name you'll see again. And Lake Superior is a natural laboratory because it's something the size of an ocean with no salinity. So that's very interesting because it means that one of the things we worry about in oceanography is not relevant in Lake Superior. And so I looked at the website of the department, and I decided I was going to talk about concepts of methods applied to the environment and water. So I felt I was within the scope of this department's mission. And so here are some names of people involved in this work. It's a long list. I won't read them all out. Just to point out that Todd Christopher and Katie Matusik were PhD students, and the rest of this cast are people who've been involved either as co-PIs or collaborators. I'll note that Jay Austin is at the University of Minnesota Duluth, and he's the one who took some of the observational data that I will show you. He's at the Large Lakes Observatory, which is a beautiful building, which is the original campus of the University of Minnesota Duluth. And this is UC San Diego, and this is Scripps Institute for Oceanography, which is a school within UCSD. And I'm going to thank the National Science Foundation later. So please don't be afraid to ask questions. There's going to be too much material, and so I'm happy to chop, remove, go with the audience's interests. So I've shown you Lake Superior, and I want to talk to you about convection. And so I'm going to talk about a number of things. I'm going to try and remind us what Rayleigh and Bénard convection is. This is a sort of canonical flow in fluid dynamics. And then talk about other kinds of convection, what I'm going to call radiatively-driven convection. And I'm going to cheat and move to periodic convection. We'll talk about that. And then horizontal convection. And I'll try and explain why these flows are interesting, what the applications are in oceanography and in limnology, I guess, and how they're different from Rayleigh and Bénard convection. So Rayleigh and Bénard convection is sort of one of the classic flows in geophysical fluid mechanics, and in general, it has applications in industry and as a canonical sort of flow. I like the word canonical. It sounds fancy. So Rayleigh and Bénard convection, I cool at the top, I heat at the bottom, and the idea then is that a water parcel that's heated up becomes less dense normally, and then it rises because gravity gives you a buoyancy force that moves the parcel up, and then at the same time, the inevitable forces of diffusion and of viscosity, entropy is trying to smooth everything out. They try and slow it down. So if I just heat a little bit, it will get smoothed out. But if I heat hard enough, I will get things to move around. And that will be one way of transporting heat in my system. And so that's very effective and very important in many, many situations, as I said, both industrial and geophysical. So here are some words to say that. This is a famous problem because one can analyze the stability by hand. This was done in the late 19th century, early 20th century. And of course, if you push it hard enough, you might expect that not to work. You'll get a complicated flow with plumes, mushroom-like objects. And people then will try to focus on scaling laws. How does my heat transfer depend on my forcing parameters? The basic geometry, though, is very simple. I have one temperature here, one temperature there. What happens? You might argue that in the real world things might be more complicated. And I'm going to talk about what happens if I try and vary these temperature boundary conditions either temporally, so I'm changing my forcing in time, or spatially. I have horizontal variations of the forcing. So I'm going to talk about them. And some things that I won't talk about here are a number of issues about scaling laws. There's a lot of contention here. You can find people who have good, long-time, 20-year-long fights about this. So I'm not going to talk about that. Instead, I'm going to skip about, on the one hand, mostly talk about stability, and then a bit about scaling laws. So just some equations here. These are the equations I'm going to use. I'm not going to write them down all the time. I'm going to remind you of them sometimes. I have a fluid. It's got acceleration. It's got a pressure gradient. It's got viscosity. And it's got temperature. It's got buoyancy effects. Gravity, if I have light or dense fluid, will make things go up or down. And my fluid is a geophysical fluid. It's not a star. It's not a gas that's highly compressed. So I make what's called the Boussinesq approximation. And my temperature just makes things go up and down. I'm incompressible. Again, I'm not highly compressible, not an Earth star. And then I got some kind of temperature diffusing around. That's really the energy equation. If you prefer, you can think of this as buoyancy. Or an oceanographer would say, you could think of it as density. And an oceanographer would say buoyancy. It's how things accelerate in the vertical. And then boundary conditions, which I'll talk about. And so there are many, many extensions of this. And the porous medium equivalent is very well known. It's very much studied in terms of a number of contexts. It has similar mathematical properties, maybe easier in some way. But I want to investigate other configurations where other things happen. So, OK, the clock is over there. And so the first thing I want to talk about is what I call radiatively driven convection. And this is a ship. And you can't quite see that, but this ship belongs to the University of Minnesota through some complicated agreement with the National Science Foundation. It actually was a fishing vessel first and got converted to do this. And this is data from 2019. The data is collected from a mooring, which has a number of thermistors as you go down the chain. And it's telling the temperature at various depths. And although it's not completely obvious what's going on here, you see that we are in the late spring period, early summer period. And so the water in the lake is pretty cold. It's at 30, 90, 150 meters. And you see there are large variations here in temperature at 90 meters from May to June, which then vanish, and then they go the other way. So initially, at the surface, I'm colder. I'm less cold at depth. And then I'm about the same temperature. So that would suggest that the entire depth of the lake is doing the same thing. And then in summer, I start to get a bit warmer. And then the top of the lake becomes warmer, and the bottom is colder. So that's over 2 months. And then over a certain day, this is midnight. So what I see is that here I go. It's the morning. Not much happens. And then I see that I get warmer near the surface. And then overnight, it kind of comes back again, and then it starts all over again. So what is happening? So what is happening is it's spring. The lake was frozen in winter, like pretty homogeneous in temperature. And then the ice melts April, May. It's pretty late. And then when the ice melts, my lake is cold, 2 to 4 degrees C. And then the sun shines, and the sun heats the top of the water column. So the depth to which it goes down, 10, 20, 15 meters, depends on how clear the lake water is. And I have incoming shortwave radiation, which heats up the top of the lake. But the problem is that in my Rayleigh-Bénard picture, where I have cooling at the top and heating at the bottom, this is what we're used to. If I cool at the top, I get dense and I sink. I heat at the bottom, I get light and I rise. On this picture, the water is below the critical temperature for water of about 4 degrees C. So water is in its anomalous regime, where if I heat it, it gets denser. So I heat the water at the top of the lake, it gets denser and it sinks, which is completely counterintuitive. But it's what happens in a lake like Lake Superior in late spring. So I'm able to convect the lake, turn it upside down and mix up the water. And for the limnologist, that's very exciting, because any connection between the top and the sediments has implications for the biology, the plankton, and so forth. So this is a very interesting question in fluid dynamics. Why does this happen? It happens because of what I've just told you. That's the mechanism. But you then want to go back and think about what is the stability property for this system? Because as I'm heating it, I heat it during the day, not much at night, during the day, not much at night. So what is happening when I'm heating up this system periodically? So that's the motivation for this problem. And this is joint work with Jay Austin, who, as I said, is in Duluth. This is Here it is. And also Alberto Scotti, who is just moving from University of North Carolina to Arizona State University. All right, so that's the first problem I'm going to talk about. And I'm then going to talk about horizontal convection. So what's horizontal convection? Well, imagine that you're the ocean. You're a very big, very thin layer of water. And someone taught you about Rayleigh and Bénard. You wouldn't be that impressed because in the ocean, I'm heating up at the equator and I'm cooling down at the poles. This idea of a constant temperature top and bottom is clearly ludicrous. In the ocean, actually at the bottom, there's not much heat flux coming through. You can look at the surface of the ocean. The sun shines. That's hundreds of square watts per square meter. At the bottom of the ocean, there's a very minor geothermal flux, 4, 5, 6 watts per square meter. It's not very important. So in the ocean doesn't want to think about Rayleigh-Bénard convection. It wants to think about convection that's forced by horizontal temperature differences at the surface. And that's been called horizontal convection. And this is an example of a numerical simulation where we are modulating the temperature or the buoyancy at the top. And you see I get a dense plume that falls down with a whole mess in the interior. So as I said, people like to talk about buoyancy, the local acceleration of fluid parcels. So this is another canonical type flow. It's been looked at for over 100 years. It goes back to a man named Sandstrom. And there's some very nice reviews by Ross Griffiths and co-authors that I highly recommend. And here some questions immediately arise. As I said, in Rayleigh-Bénard convection, we like to think about the heat flux, because as I force my system, I expect a transition from a diffusive heat flux to a convective heat flux. So that's a very important question. In this horizontal buoyancy system, well, the vertical heat flux is not relevant because it's zero through the base, so it must always kind of be zero because it's conserved. There's no source in the interior. So instead, you want to understand how heat is redistributed in the horizontal through the system, but it's not obvious what the right measure to use is. So that's one thing I'll talk about. And then I'll talk about scalings. So as I said, Rayleigh-Bénard, we got zero net vertical. We got heat flux coming through. There's a Nusselt number. Horizontal convection, no heat flux coming through. I had a former student, Katie, who did experiments on this, and she was interested in the overlap of mechanical and salinity forcing. She had a big tank where she could introduce a saline source of fluid. This is not working very well. Here we go. And she also had mechanical forcing. She was flowing water over the top. This is her apparatus. It was pretty big. It was a meter long and 50 centimeters tall. She had to insulate it and keep it cool. And she got pictures like this. She was able to analyze the circulation to understand the interplay between the saline forcing and the mechanical forcing. You form a plume that falls down the side. I won't go through the details. She put together a recycling box model. What I want to say is the experiments were slow and difficult. She spent months in the lab, cameras, calculations. And today I'm going to talk about some theoretical ideas. So we'll bypass experiments and talk about fundamental questions. Okay, so that's the setup. So I'll try and talk a bit about radiatively driven convection and horizontal convection, and then some ideas at the end. So this was in Todd Christopher's PhD thesis. And what he's done here, he's written down all the non-dimensional parameters. So we recognize some of these. We recognize the Rayleigh number. That tells you how hard you're forcing the system. It's the ratio of buoyancy to diffusion. We have the Prandtl number. That's a property of the fluid. We usually think about 7, but it's more like 11 because the water's so cold. And then we have some other properties. This is what you see in normal Rayleigh-Bénard. Look at the Rayleigh number. You look at the Prandtl number. The Rayleigh number is very, very large in the lake, 10 to the 20. And then we have other parameters. We have how fast we're forcing it. What's the modulation frequency, which is called omega. So that's like a ratio of oscillation to diffusion. You have a time scale. If you think about the Stokes layer at the top of a fluid that's being oscillated, you have a boundary layer thickness, you have a diffusion thickness, you get this parameter. And we have also radiative heating. How far down the water column does my sunlight get to? And if you looked at the equations I showed you, the source term basically looks like this exponential. It decays exponentially with depth. So I'm going to cheat. We're going to basically assume that all the forcing is at the top. So to understand the effect of gamma, which is fairly small, won't have to go back and do some more work. I just have one slide that shows that. What do? We force it at the top. You can argue, are we forcing it with the same temperature or the same buoyancy flux? How much heat I'm adding? This is probably more realistic because it's like having a source and compressing it to the top. And the last thing I'll say is that the modulation frequency is very, very large in our system. because basically molecular diffusion is very small. That does beg the question that in practice we expect transport to be dominated by large-scale processes or by an eddy diffusion, if you imagine an analogous system in turbulence. And so this is mathematically correct, but you might worry whether in reality we should be having some kind of turbulent version of this. But how do we quantify that? So that's something that we haven't tried to do. OK, so let's talk about stability. And so you may worry that this is not necessarily very relevant because the Rayleigh numbers 10 to the 20. And I would agree, but we should start somewhere. And so stability is where we're going to start. So what is stability? And this goes all the way from fluid mechanics to dynamical systems to solid mechanics. It's what happens if I disturb some kind of equilibrium of a system. So normally my equilibrium is steady. Here my equilibrium is some kind of periodic disturbance. And so what you do is you perturb it, you see what happens. And there's normally two things you can do. You can look at linear stability and nonlinear stability. So nonlinear stability says what happens. I have no convection. Linear stability says I start convection. I have a teeny-weeny disturbance, and it starts to move. Nonlinear stability normally is about, can I stop convection? What's the highest I can force it before something happens? And Todd was a history major before he did some engineering. And so he likes to think about there's no revolution, and your control parameter is the price of bread. The question is, are you trying to start a revolution? That's linear stability. Things go bad. Or are you trying to stop a revolution? That's nonlinear stability. Things can't go bad. And if you think about the picture, what that means is that if your Rayleigh number is here, there's a region below which it doesn't matter how hard you push it, you can't get a revolution. And there's a number above which, if you push it, you will definitely get a revolution. And in the middle, you don't know what's going to happen. So you might have some steady states, some subcritical instabilities, and that's something we haven't really investigated there. And so one of the properties of Rayleigh-Bénard convection is these two thresholds are equal. The linear stability and the nonlinear stability criteria are the same, which is not obvious ahead of time. In the problems I'm going to show you, these are very different. And this is also the case in turbulence, where people talk about edge states and objects that exist between the linear and the nonlinear stability regimes. OK, so linear stability. How hard do I have to hit it so that if I ever so slightly touch it, it'll blow up? Well, this is how you do it. You take a base state. You have a perturbation. You throw away nonlinear stuff. You get equations for these little p's. And then you check whether they grow in time. So if they grow, if they're exponentially growing, so the real part of mu is positive, you say it's unstable. If it's negative, it's stable. In Rayleigh-Bénard convection, all that matters, there's a t missing there, is the background state, and its gradient is a constant. There's always the same. Background state is diffusive. It's just linear temperature profile. And the problems I'm looking at, it's more messy, but it's still the same equations. So this sounds terrific, but you might be rather suspicious of how this works if my background state is modulated. Because we think about taking the equations, we do our linear stability analysis, we say the coefficients are independent of x, independent of y, independent of t, and get exponentials. This is not the case in my setup. And so that's why one uses what's called flow K theory, which is the theory that looks at the perturbations to a periodic system. So we're saying I force my system periodically, sun shines, cold at night. We cheat. We assume it's a sinusoid rather than a real profile that would shine, then cut off, and shine, and cut off. And then what happens is there are theorems that tell you that you get a growth rate, exponential growth times a periodic function in time. So we're back to the same game of playing mu of t. Phi is a periodic function, and that says that everything can be decomposed into Fourier series in times, and I get a whole bunch of coupled systems. So these are the equations you get. This is this essentially is the, there we go, buoyancy equation and the vorticity equation, and you get an infinite number of coupled problems. So numerically, you're faced with a problem that you have to discretize an ODE with a whole bunch of modes. So even though you've got one single forcing mode, cosine t, you get infinite number of coupled systems. So you have to truncate them and decide what order to truncate and play your usual games with discretization. But this is what Todd did. This was his thesis, one of the things he did. And you get these large eigenvalue problems, which are numerically problematic. But you can solve them, and you find some interesting results. Now, let me talk about nonlinear stability, then show you all the results on one slide, or a couple of slides. And so there's a very nice link, because there are two beautiful books by Dan Joseph, who was here, about nonlinear energy stability, which I highly recommend. So the idea here is you say, all right, I've got a base state, I've got a fluctuation. I look at the energy. So for Navier-Stokes, it's the kinetic energy. For Rayleigh and Bénard, it's a combination of velocity and temperature. You play around with it a bit. And then you can show that if you set the thing up properly, you can have a critical value of the Rayleigh number, and the energy always decays. And this is fully nonlinear. Nothing's been thrown away. You get a variational problem, and you can show that under certain criteria that works. But in fact, you may not need to do that. You may need to say, well, my system is periodic, and so over a period, it can't grow. It could grow a bit and then decay a bit. It could grow a bit, then decay a bit. But on net, it doesn't grow. And so these are called strong global stability and asymptotic nonlinear stability. And so Todd also did this for the system. You end up with a linear eigenvalue problem, which is actually rather nice to solve. But then you have to maximize something over the minimum over the minimum. So there's a whole optimization problem to do. Conceptually, you solve one variational problem. OK, so that's what Todd did for his thesis. And this is what it looks like. And I'm going to show a movie in a second. So this is a picture that you may have seen. It's in various textbooks. I have the Rayleigh number, and I change the wave number because my system is invariant in the horizontal. And if I'm above this Rayleigh number, I get linear instability. The disturbances blow up. So this is the no stress boundary condition, no slip boundary condition. This is Rayleigh Bénard. And this is not what happens if you've got modulated Rayleigh Bénard. So in modulated Rayleigh Bénard, you get values that are higher, and where you have different colors depending on how your instability behaves in time. I've got a movie of this, which I hope I can show. It's over here. So this is what happens as you vary the frequency. So you see that as you vary omega, you get a whole bunch of lobes, and there's a very complicated structure as to where you're stable and unstable. And the colors correspond to what the phase shift is or what the periodicity is of your periodic function. So let me try and go over that a bit. When you look at this stability problem, you have a periodic function and you have a growth rate. And what you care about is what the real part of mu is. Is it positive or negative? And there's also an imaginary part which tells you whether there's an overall modulation that is slower than your period, which would be subharmonic or the same as your period. And you don't know that ahead of time. You have to solve for it. So that's what these red and purple colors correspond to. So sometimes you call them synchronous modes, sometimes subharmonic modes. And we're starting to look a bit like parametric subharmonic instability, which is very relevant to structural problems. That's the child on the swing. The child kicks his or her legs out, tucks them in twice in a period. And that boosts parametrically the amplitude of the swing. So this is related to the imaginary part of mu. So Todd solved this problem and was able then to obtain the critical Rayleigh numbers for growth, both for linear and nonlinear instability. This is no slip. Yes, sorry, go ahead.
Sorry, I didn't understand exactly where the wave number is involved.
Okay, yes.
What is the physical meaning of the wave number?
So we have a system that is invariant in the horizontal, and we're looking at the response to every wave number, and you're allowed to pick that. Even in the nonlinear case, you optimize over the wave number. So in the linear case, you get a bunch of horrible equations, and the wave number just comes in here. So it's a parameter of your problem. If I have this wavelength, what is the growth rate? In the nonlinear problem, you have to do a optimization problem over the wave number. So you get a global number and then a value for each of those wave numbers.
Okay, so the perturbations are decomposed both in space and in time.
Yes, for the linear case, they're decomposed in space and time with just a very standard for it. Well, decomposed in time is tricky. You have a periodic function times e to the mu t. In the nonlinear case, you're optimizing over time and k and everything. So it's decomposed, but it's really an optimization problem. And so if I look at the nonlinear case, there's a whole optimization thing you don't see because I've just filtered everything out, and all that's left is omega. So here I'm telling you the lowest Rayleigh number for all k for this problem, and for the nonlinear case, it's what you get from the optimization.
Okay. Thank you.
So you see that we have this linear curve, which has to be above the others. Doesn't make sense otherwise. The colors correspond to whether it's synchronous or subharmonic perturbations, and the nonlinear curves are below. So if I'm below this black line, every every disturbance will decay at every moment in time. If I'm between the black and the blue line, I'll decay over a period. If I'm between these two, I don't know what's going to happen. If I hit it hard, it might go unstable, but I can't guarantee it. And above this jagged curve, if I hit ever so slightly anywhere, it will blow up. So we see our possible existence of subcritical states and a big separation between these three curves. And we also see that for small omega, it's very, very hard to calculate this. It becomes numerically very problematic, whereas the nonlinear case is very well behaved. So our Rayleigh numbers for no slip are much higher than no stress, which is very common. If I'm no stress, I can slip on the boundary, I can grow. If I'm no slip, I'm slowed down by my boundary. So here we have our three curves. There's an issue with what this curve means, which I'll come back to. So then you can say, all right, what if I look at small omega? This is a bad limit for the ocean, for the lake, where omega is very big, but mathematically you like to understand it. And you see that your curve becomes very messy and that the critical wave number jumps around. So there's some kind of modes that switch on and switch off. What I'm showing you are various approximations. The numerics stop about here. We've been able to do an analytic limit for very special boundary conditions, but we don't know how to do it in general. And it leads to matrix WKB problems, which are very badly explained in the literature, and where there's a fundamental problem, which I can discuss later if you like. And there's also a philosophical issue. It's not clear this is a very sensible non-dimensionalization. If you're saying your disturbance has a shorter and shorter period, what does it mean to have any period? Because either I'm at the top or at the bottom. It's a very strange limit, which I'm not convinced is a good limit to look at. But Todd worked very hard, and he got omega down to about, the blue thing goes to about here, about 3. Couldn't go below that. So mathematically, there are some interesting questions. Oops, does this going to do anything? Then you can also scale it for large omega. This is very relevant for the lake. Turns out you can construct a natural parameter Rayleigh over omega squared, which basically throws away the depth of the lake. If you expect the lake to become very deep, it should only know about the boundary layer at the top. That's the relevant Rayleigh number. And you see that your linear curve asymptotes very nicely. So this presumably means that for very large omega, this will still be the limit.
Is that power minus 2 obtained by a rational argument?
Yeah, it's obtained by dimensional analysis.
So it's absolutely definite.
Absolutely. But this is what I don't understand. It doesn't seem to work for the nonlinear case. I don't understand that. Because dimensional analysis, this is the parameter that throws away the depth of the lake. It cancels in Rayleigh and omega goes up to minus 2. So what happened in the nonlinear case, I don't understand.
But you know the scaling of the nonlinear term.
Well, we haven't spent a lot of, we could try and work out from this the power of omega. So maybe it's asymptotics of the second kind. I don't quite know what's going on there. It's a very interesting question. Well, we could talk about that, because I don't understand that. And when I say matches semi-infinite domain, it just means taking a bigger and bigger depth numerically. Does the bottom matter? Well, this is where Todd did all 16 combinations. The answer is it matters a bit, but not as much the difference between linear and nonlinear cases. It's not a very exciting graph. And then finally, one can play with the Prandtl number. Again, the lake is here. You see very interesting results for small Prandtl number for the linear case, whereas the nonlinear case is much less sensitive to that. So the real lesson here, I think, to me, is that the linear case is, I wouldn't say pathological, but has real problems in terms of how to interpret what the calculations tell us. Trying to work out what time it is now from that clock. Okay. And then we also did the case with actual radiative heating, where we have a non-zero value of gamma. So that, if you remember, is the depth. And so if you look at your value of gamma, if you look at the value, the result you get with the dashed line is what happens if you just say it's all at the top. And then if you make gamma non-zero such that the amount of integrated flux is correct, you see that the values change by about 10%. So our approximation of taking basically gamma as 0 seems to work quite well. So we're not too worried about gamma not being exactly what happens in the lake. Now, this works. One thing that Todd didn't do in his thesis is he didn't do large numerical calculations. So I was talking to a colleague, Michael Lebas, who was interested in this problem. And he went off and did some calculations. So I should have put that this graph is from Michael. So he took certain values of Prandtl and omega. And he said, OK, if I'm just above the linear Rayleigh number, what happens? Just below it, way below it. So if he's just above it, you see that you grow in a nice exponential fashion. This is a logarithmic plot. And so we do have linear exponential growth of the kinetic energy. If we're just below it, then we should have something that could potentially oscillate but would decay. And you see that, in fact, it does oscillate and decay. And if I make it very far below, it should decay at all times. And it does. It decays in time. So there's a lot left to do with DNS. In particular, can we get nonlinear subcritical states? Can we understand how that behaves? So there's a whole bunch of things for future to be considered. OK. So the next thing that Todd did, and this comes back to the work on Rayleigh Bénard, is you say, well, all right, my system is clearly unstable. My lake's got a ridiculous Rayleigh number, 10 to the 20. Why were you worrying about things going unstable at Rayleigh numbers of, I don't know, 10 to the 8? Well, not 10 to the 8, more like 10 to the 5. We're way above that. It's clearly turbulent, total waste of time. So then you'd say, a mathematician would say, well, that's true, but we can get bounds. We can prove how certain quantities evolve or are bounded. So you give me a lake with Rayleigh number 10 to the 20. I say, all right, I'm turbulent, but I know what the Nusselt number will do. So I learn something. So there's a whole literature on bounding. And so the question there is, what's the heat transport? And if someone tells you there's no motion, that's pretty easy because you just work out a diffusive flux. If you've got motion, that's much more difficult. But you can actually produce rigorous bounds. You take the full nonlinear equations and you set up a variational calculus problem to bound something you care about, which in our case is normally the heat transfer. So the problem is, for Rayleigh Bénard, the heat transfer is very simple to write down. You've got relations between the Nusselt number and other quantities. For the things that we care about, the only thing you can really deal with is the variance of temperature. And that's not actually anymore the obvious Nusselt number, but we're still going to use it because we don't know how to do anything else. And so you then set up what's called the background method of Döring and Constantin. That goes back to ideas from Howard and from also going back to Hopf. And you can then modulate the temperature. And that had never been done before. The closest was a paper by Mark Euro, who'd modulated shear at the top. And I will spare you the details. You can compress it into 3 pages. Very dense. I'm not going to show you, I'll show you some equations. But the point is, this is fully exact. This is true. Any flow in the real world, if it obeys the appropriate Navier-Stokes-Boussinck equations, must satisfy this. And you can show that your temperature dissipation is bounded by a number of messy objects which look like square root of the Rayleigh number and square root of the frequency. And so this recovers the standard steady result, where omega is small, but also tells you if you oscillate it very, very hard, how you scale with omega. So these results should be satisfied by any numerical calculation and by any measurements, although it's not obvious how you'd be able to measure grad t squared in the real lake. This quantity you'd have access to in numerical simulations. The thing to realize is that this bound here is not necessarily sharp. In fact, for Rayleigh Bénard, we know it's not sharp. There's a big fight as to whether it's more like this power or that power. We've done the best we can here. Maybe someone will beat that bound. I don't see how to beat that square root. Seems to be unbeatable. But it was nice to see for the first time an exact result with modulation built into it. All right, so what did we learn? We learned this was very different from Rayleigh Bénard. We had to use flow K theory. We had a difficult numerical problem for the linear case, but the nonlinear case was quite well behaved. We don't quite understand its scaling for large frequencies, and we're able to bound some quantities. So we've learned something about periodically forced convection. Sometimes I say radiatively driven convection, but really this is periodically forced. We kind of put the gamma, put all the radiation onto the boundary. So that was my story about periodically driven convection. And I've lost track of the time here. When did we start? 10 minutes? OK. So let's talk about horizontal convection, which is going to be a bit more qualitative. So this is the idea. I take the same equations and I force them at the surface, and I get flows that look like this. Where it's cold, my flow sinks. Where it's warm, it rises back up. One very important difference is that in Rayleigh Bénard convection, I have a solution that is just diffusive. It's just cold to hot, sits there. Horizontal convection, if I change the temperature at the top, there's no steady solution. As soon as I turn the temperature on, it moves. So there's no linear stability problem. And so in this discussion, we talk a lot about averages. We integrate at a constant depth. We integrate over the whole volume. And you can show that you can relate the dissipation of kinetic energy, which is epsilon, that's what you see when you work out the kinetic energy equation, to the conversion between potential and kinetic energy. There's an overall conservation of energy. So if you're losing kinetic, it must become buoyancy, and you can dissipate some of it. And there's what's called the Anti-Turbulence Theorem, Paparel and Young, that says that in horizontal convection, you can bound the dissipation of energy, which leads to all kinds of questions as to whether this is a turbulent flow or not, which I will not talk about today. But a very major question comes up. Is this going to do anything? Yes, here we go. It's what's the Nusselt number? So you might say, I want to understand how heat flows through my system. But I know it's not going through the top because I know there's no net vertical heat flux at any depth. So you say, well, but if I got hot and cold, I'm moving fluid around, so there must be horizontal heat fluxes. So you can define a horizontal heat flux like this, J of x, but then your problem is it depends on x. So what does that mean? It's not a measure for the flow, it's a variable. What you can do, though, is you can relate this J, its gradients, to a buoyancy flux to the top. And I've shown that this works very well. I won't dwell on this in detail. And at the end of the day, when you go through it, you can show once again that this object, the gradient of the buoyancy variance squared, which seems a very abstract object, on the one hand, it has good mathematical properties. We used them previously. But you can show that this object is an index of the horizontal buoyancy flux. It relates the correlation between your gradients at the surface and your fluxes in the horizontal. So it's a very useful object to use. And you can also compute it a different way over the surface. So this is useful because it means that you can diagnose it from a surface expression rather than integrating everything over the boundary. And it means that this mathematical quantity, which seems rather abstract, is also useful to use for data analysis. It turns out by looking at this, you can also define effective diffusivities. So this is a bit like turbulence. I have large-scale gradients. In reality, I've got complicated small-scale flows, which can go up large-scale gradients. You can work out an effective diffusivity as this average, which I won't show you today. And the other good thing about this is that this quantity stabilizes, equilibrates very quickly. So you run a simulation, and you have long timescales. These are timescales on the diffusive length scale. It's very inefficient to do these long calculations, but the Nusselt number equilibrates very rapidly, much faster than the kinetic energy. So you can run a simulation and get a pretty good idea within 0.2 of a diffusive timescale as to what it's converged to. Whereas this kinetic energy thing is taking much longer and oscillates much more. So that's a useful object to have. And then the last thing I'm going to talk about, I want to give time for some questions, is I spoke about bounding. And you can try and do this for horizontal convection. There's a paper by Siggers, Kurzweil, and Barnforth, which gives 1/3. And I'm not going to tell you about this, but we spent pages and pages reducing this bound by a factor of 2. So maybe that was a quixotic endeavor, but it's a very interesting mathematical object to look at. And you can do all of this by essentially introducing comparison functions. You never actually solve the problem for the full equation. You can take a fake function that looks like this, that looks like what you want, and you can turn the equation so that everything you do is a variational problem for this big C variable. So that's an extraordinary calculation. It goes back to ideas from Young and Winters and Young. We're able to load this, but what was interesting is what it looks like. So in this picture, I'm showing you the temperature variation on the surface. This is the red curve. And then when you try and optimize this bound, you find that the eigenfunctions are highly concentrated in space with enormous wiggles. And so if you think about it, that means that mathematically they're problematic. Your limit of infinite Rayleigh number is going to become a bunch of delta functions. So your model is not very good there. But it makes you realize that presumably these very efficient modes that move temperature through your system are very concentrated in space and have these wiggles in them, which is an interesting conclusion. So what did we learn? Well, I went through this quite quickly, but this horizontal convection problem that just changes your boundary condition to one thing on the surface leads to very serious questions about how to define the Nusselt number. I think we got around that, and you can try and do scalings and bounds, and you can make some progress, but we still fundamentally don't know whether this 1/3 is sharp. Not clear at all how we could possibly beat that 1/3. Okay, so to finish up, I want to show some conclusions And there's some current work which I hope some of you find interesting. All right, so what else could one do? Well, we have this rich system. There's a whole thing that we haven't yet done for the periodically driven convection. You could add rotation. Alberto-Scotti's simulations suggest that could be important. Often in oceanographic situations, it's not important because everything is very small aspect ratios, but for Lake Superior, the depth and the scale of the convection are not that different, so that's an interesting question. You could try and do more nonlinear stability methods that go beyond energy. It's not clear how to do that. That's a long-term project for other people. And I think the real question is, this thesis was a lot of great work by Todd. The difficult part now is going back from this back to observational colleague. What does this mean about the lake? What do I learn? I think the answer we learn is we have to do more simulations to try and find these subcritical states. And in particular, some quick numerics suggest that we can get this phenomenon where overnight the lake seems to reset. So you look at this problem one day, you measure, the next day it's about the same. You start off with a very small temperature difference, it turns over, becomes stagnant, and then does the same the next day and gradually heats up. And then for horizontal convection, we're looking at some things right now. One is the boundary layers and scaling laws. I'll show you a picture. And the second is there are some interesting basic states. I told you there were no basic states because you drive a flow, whatever happens. Turns out you can cheat and find some interesting basic states that we're looking at. Okay, so this is the current question. If you do, these are 3D simulations. I'm showing you a snapshot. If you do this and you push the Rayleigh number, you get complicated patterns with vortices moving around, and the flow is falling down in the middle and turning over. This is the scaling you get. This is the Rayleigh number. This is the Nusselt number. Define the way we've said it. This rate to the 1/5 is what was predicted by Rossby and by other arguments. We seem to see rate to the 1/4. And at the moment, the question is, can we explain that? We have a nice vortex gas argument. But the problem is that if you look at the boundary layers on the top and the bottom, this is a boundary layer scaled by the Rossby boundary layer thickness. You see everything seems to be on the right scale. But as you look at high derivatives, there seems to be a jump near the top, which seems consistent with this radius to the 1/4 boundary layer, which means you've got to differentiate between a radius to the 1/20th on these things. So we're kind of at the moment trying to work out, can we actually rationalize this boundary layer? So I'm basically done, but I can't resist this because John Chapman's in the audience. So these are calculations with Michael Lebas and Bill Young. You have a nuclear safety problem. You have a cylinder or a disk. You heat it from the bottom. You don't take as much heat out of the top. How much goes to the sides? Numerical calculations show you that the vertical velocity lives in boundary layers. The temperature in the middle sort of parabolic. And then you have a large-scale flow. And you can find a nice high aspect ratio solution asymptotically. The blue is an average numerical solution. The dots are the prediction. So I felt pretty good about that. But then what one needs to explain is an instability in the transverse direction, which we haven't been able to explain yet. Well, that's what we're doing right now. So I'm going to wrap up. Thank you for the opportunity to give this talk. I hope I've told you things about convection you may not have seen before. These are some of the references. I'm happy to discuss them further. And these are some pictures from July 2021 of us out on the Search Vessel Blue Heron. So I'm going to stop there and take questions. Thank you very much.
Great. Thank you, Stefan. We are open for questions. I don't know if there are online questions. Not yet. Okay. Please. Okay.
That was very fascinating and lots of food for thought. I was thinking about when you were asking about lessons learned. It seems to me that some of the calculations you were looking at could be predictive type tools for looking at what might happen under climate change scenarios, especially as the equator gets hotter or colder. I'm not quite sure what would happen. Is there some potential in there, especially with the horizontal convection model, that you might see some changes in ocean circulation due to the phenomenon that you're looking at?
Well, that's one of the motivations, of course. We have this age-old quandary, which is how realistic a model does one produce people to believe it, and what one can manage with the technical sides. So we haven't tried to relate these flow patterns to how they might change under changes in the forcing. But that is ultimately one of the questions is, is this a good explanatory model? Do the scalings help us understand what might happen at the climate scale? So we haven't done that yet, but that's one of the underlying questions, of course. can one from this learn something you can apply to a real situation?
Here. What do you mean by subcritical instability?
Ah, okay, yes. So let's try and find the right picture here. I don't know a faster way except skipping through this. What's the picture? Here we go. So in this kind of picture on the left, which is a sort of usual picture we see when we do introductory class about hydrodynamic stability, if I'm below this curve, I'm stable linearly. If I'm above it, I'm unstable. And that's it. There's no other weird behavior going on. In this kind of curve, over here, there may be exact solutions. So the problem may be that there are multiple solutions of my nonlinear equations of motion, and how do I get from one to the other? They could be steady solutions that are not connected to the original branch I had, which I have to then try and recover how to get back to it. So there may be situations where there are other exact solutions, and I haven't been able to find them yet. And there's an extensive literature for Navier-Stokes, for Quet flow, for rotating Quet flow, and so on, where people find other exact steady states, and they're conceptually interesting. People like Kurzweil and others have used them as ways to describe what they call edge states of turbulence. That turbulence is maybe a set of configurations where you go near these basins of attractions for these steady states and jump from one to the other. So that's something that we haven't found here yet.
I have a follow-up
Yep.
question. Do you mean there is convection below the critical Rayleigh number?
Here, well, yes, here there could be situations where you could get convective flows that don't just die out. But they can't live below here. That's not possible, but they could live here.
So yeah, just so in this marginal stability curve,
Yep.
you do have some instability for specific wave number.
Yep.
And is there anything? So these modes should be present in the geophysical
Yep.
flow, right?
Yep.
So is there any kind of experiment or field observation where you recognize those special patterns that
Okay,
emerge
so
from your stability?
So that's a good question. So the problem is that the lake is way too big. So we're so far above this. So one thing that we looked at is whether the length scales we predict here, you can't see it because this is, optimized over all the wave numbers, but whether the most unstable wave number is the one that seems to match up with the observations. The problem with the observations is you put down a couple of mooring chains. There were some horizontal moorings. We don't really have a good handle on the horizontal length scales. The LES that Alberto is doing sees some length scales. They tend to grow to the size of the box. So at the moment, we don't have ways to compare the prediction of the linear theory to the observations. I don't think they're relevant. I think there's a nonlinear problem. Maybe this nonlinear prediction is relevant. Maybe there's some complicated nonlinear system. And so there are systems where you switch them on, and then these modes then coalesce. You get coarsening. You get Kahn-Hilliard type equations. The answer is we don't know. Are there numerical experiments? Well, that's a bit what I was showing you at the end. Todd didn't really do that in his thesis, but here one could try and do some calculations and see if this linear pattern then evolves to a different length scale or what happens. So that would be a very interesting thing to do. Probably the most important thing is, do these linear length scales, as you increase the Rayleigh number, do they mean anything at all?
Thank you. Thank you.
Any more questions? Okay, Jim, just a sec.
Do I keep my mask on?
You can.
I have to keep mine. Right. Well, thank you, Stefan. At the beginning, you said there were too many parameters.
Yes.
But I wonder if that fits into with what we were talking about just before this talk. That by introducing relations between them in the form of power relations, where initially you don't know what the powers are, but you then find them by a dominant balance argument where you try and balance as many terms as possible. And I believe in that situation you get some reasonable number of balances. But I wasn't quite clear whether you'd done something along these lines already. You had a power of a third and various other omega to the -2. So it seems to me you were in that direction already, but you could be completely systematic and probably find a lot
That's
with a little code.
Yeah, interesting question.
And that that might resolve some of the problems.
Right, so we were talking about this earlier.
Yeah.
The parameters omega and gamma, one of them lives inside a cosine, one lives inside a z, whatever. So I'm not quite sure how your theory technique
Well, every time
works.
you have a derivative, you bring down.
Okay, I see.
It's the kind of stuff that you and I
Right.
are doing really as undergraduates, probably.
Well,
And you
there are,
mentioned at
yes,
one point-
that's an interesting question. Yeah,
Yeah.
it'd be fun to talk
Yeah.
about that.
And you mentioned at one point the scaling with omega was
That I
peculiar.
do not understand,
So
yes.
wasn't quite sure. Do you think it might be mistaken in that you might need some other term? Or do you think it's definitely correct?
That's
that
this
peculiarity
curve.
is something to
That's this
work
curve
with?
here. That I don't know. It would be interesting to do some numerical calculations to see if that's confirmed. This was completely what we expected, just based on dimensional analysis.
Yeah.
This, I honestly am not sure what it means. It seems to, well, maybe it means the following. It seems to imply that you can never ignore the bottom. And maybe that means that in this full nonlinear process, when you're optimizing over everything, there's some solutions you're optimizing over that still know about the bottom. That's my sort of
But if
only
you can
naive
never
guess I
ignore
have.
it, however far away,
Well, but that's
that
right,
just
but it
suggests a
seems-
singular limit, doesn't it?
It
The kind of
does,
stuff
yes.
You and I were brought up
Yeah,
on.
well, so
And
maybe
you have to find how you describe that limit by the appropriate powers.
maybe you can solve that for me.
Yeah.
That'd be great.
Very, very interesting.
Thank you.
very much.
Okay, I use Llewellyn Chapter, who is an assistant professor here, so you can, for 2 weeks, so you can communicate with him. Any more questions for Stefan? If not, please join me in thanking him for the interesting talk.
Thank you.